This is going to be the first integration technique that you are going to learn, okay? When you take Calc 2, you're going to learn some more integration techniques. We do know how to integrate some basic integrals, like the integral of cosine is sine, the integral of 1 over x is ln of x, integral of e to the x is e to the x. So those are all very basic integrals. You may call the power rule one of your first integration techniques, how to undo the power rule, but I really don't count that as a technique. This is the first one. Now, the substitution rule is to undo a chain rule. Oops, forgot the I. This is to undo the chain rule. Okay. Another way you may hear me call it use substitution. Okay. So for this substitution rule, let's go ahead and see what it says. It says if u is equal to g of x is a differentiable function whose range is in interval I and f is continuous on I, then the integral of f g of x times g prime of x, if you remember, this is what the chain rule looked like. F of g of x times g prime of x. So what this is saying is if we could rewrite our inside function as a u, what I'm going to do now is I'm going to differentiate with respect to u, and I'm going to get g prime of x dx. So what we can do is we can make a substitution. Instead of g of x, I'm going to write a u. So this is going to be integral of f of u, and if you notice, g prime of x dx, g prime of x dx, that's going to be du. So what the substitution rule is saying is that if you have a chain rule, okay, and you can make this substitution, then what you can do is rewrite the integral, because this is going to be difficult to integrate. We could rewrite it upon a change of variables here, and this will be easily integratable. Okay, so that's what we're going to do. We're going to choose what our inside function is. We're going to plug it in everywhere we see our inside function. We're going to take the derivative and then end up plugging it in and then integrating this. Okay, because that is going to be a lot easier to integrate. So let's go ahead and see some examples. So the first example, integral, these are indefinite integrals, of 1 minus 2x to the 9th power dx. So let's go ahead and take a moment to, first let's take the derivative of this. We don't need the derivative, but I think it gives you good insight of what we are doing when we do the substitution rule. If I were to take the derivative of this, the power is going to come out front, 1 minus 2x. I'm going to drop one power, and then I have to remember to take the derivative of the inside. The derivative of this inside right here is negative 2. So when I integrate this, if I had some function before, when I took the derivative of that function, I'm going to end up with some derivative of the inside. I got to take the derivative of this inside. I should end up with a negative 2 somewhere. So I got to account for that when I integrate this, and that's what use substitution helps us do. It also helps us account for these coefficients that come out front from differentiating. So if we're going backwards integrating, we're going to have to go up one power and then divide. So let's go ahead and do the use substitution. So we're going to let u equal 1 minus 2x. And then I'm just going to take the derivative of this. Du is equal to negative 2 dx. Now I'm going to make these substitutions. Instead of writing 1 minus 2x, 1 minus 2x is equal to u. So this is going to become the integral of u to the 9th power. And what I want to do is I want to substitute dx into here. Okay? But I don't have dx. What I need to do is I need to solve for dx over here. So I'm going to divide both sides by -2. I get -1/2 du is equal to dx. So now what I'm going to do is I'm going to take this part right here and plug it in for dx. So this is multiplied by -1/2 du. So this is the integral -1/2 u to the 9th du. So we just rewrote this integral in terms of u upon this variable substitution. Now, as you can see, this is very easily integratable. It's just undoing the power rule. So we got -1/2. I gotta go up 1 power to the 10th power. And then I gotta divide this coefficient by 10. And don't forget your plus c. So we get a final answer of -1/20 u to the 10th plus c. I apologize. I don't mean to say final answer. That's not our final answer. We get an answer of -1/20 u to the 10th plus c. Now, the original question asked us our integral in terms of x. So we have to take the u, plug it back in here to get our final answer. So we no longer need this. So this integral is equal to -1/20, 1 minus 2x to the 10th plus c. As you can see, all I did was substitute my u back into here. So this would be the final answer. Now, you could always take a derivative to check yourself. Let's go ahead and take the derivative and see what we get. If we get back with what we originally started, then we've got the correct answer. So, -1/20, power will bring the 10 out front, 1 minus 2x to the 9th power, got to drop 1 power, but then multiply by the derivative of the inside. The derivative of the inside is -2, as we saw earlier. Every time we take a derivative of this function here, a -2 is going to come out. So we got 10 times -2 is -20. -20 divided by -20 is 1. So all we're left with is 1 minus 2x to the 9th power. So as you see, by taking the derivative, we got back with what we started with, meaning we do have the correct answer here. As you can see, when we took the derivative, this -2 popped out. Here's where this -2 is being accounted for in the u substitution. We get it right here. Let's do another example. The process on a lot of these are the same. You state u, you get your du, you substitute, then you integrate. So let's see. We've got integral of x over x squared plus 4. Now, if I were to take the derivative of this denominator, I would get 2x. Well, that looks like the numerator, because if I were to take the derivative of the numerator, you just get 1 that looks nothing like the denominator. So I'm going to choose the denominator to be my u. U is equal to x squared plus 4. So now when I differentiate, you get du is equal to 2x dx. Oh, I forgot my dx right here. Now, I'm going to solve for dx here by dividing by 2x on both sides. So I get a dx is equal to du over 2x. And what I'm going to do now is, instead of this, I'm going to write u, because that's what u is equal to. And instead of right there, I'm going to write du over 2x, because That's what dx is equal to. Let's see. This becomes the integral of x over u times du over 2x. Now, if you notice, the x's go away. Every time you do one of these u substitution problems, your x's should always go away, and you should just be left over with u's. So this becomes the integral, there's a 2 down here. I'm going to bring the 1/2 out front. du over u. Well, this is like 1 over u to the first power. 1 over u to the first power, if you were to integrate that, 1/2 out front, you get the ln of u plus c. If you were to take the derivative of that, well, here's the 1/2. You get 1 over u. 1 over u. So now what I'm going to do, I'm going to take this, I'm going to plug it back in for u. So we get a final answer of 1/2 ln x squared plus 4 plus c. If we were to take the derivative of this, let's go ahead, this is going to be the last time I take the derivative to check the answer, but let's go ahead and take the derivative. We got 1/2 times, this is an ln function. Ln function is 1 over whatever's on the inside times the derivative of the inside. Derivative of x squared plus 4 is 2x. Well, this 2 and the 1/2 cancel, you get x divided by x squared plus 4. Exactly what we started with. Let's look at the next problem. It's the integral from x squared e to the x cubed dx. So here, if you look at x cubed, if you take a derivative of x cubed, you get 3x squared. Look at that, you have an x squared out front. If I were to take the derivative of x squared, you just get 2x. Well, 2x is nothing like x cubed, so this should tell you this function up here, u is equal to x cubed. That's what your u is in this case. If I differentiate, you get 3x squared dx. So I'm going to solve for dx. You get du over 3x squared is equal to dx. And now I'm just going to take this piece, plug it in for dx, and this piece, plug it in for x cubed. So let's see what we get. Integral x squared e to the u times du over 3x squared. So just plugging everything in, and if you notice, the x squareds cancel, and you get a final indefinite integral. There's a 3 here, 1/3 e to the u du. Integrating exponential functions is really easy. 1/3 e to the u plus c. That's all it is. Now, I'm going to take my u and plug it back in there to get the final result, okay? Because my integral was in terms of x's. It's not in terms of u's. So the final answer to this problem is 1/3 e to the x cubed plus c. Let's see, if you were to take the derivative of this, well, any exponential function, you get the same thing, times by the derivative of the inside. The derivative of this x cubed is 3x squared. Well, there's your x squared. The 3 and the 1/3 will cancel. See, let's do another example. Like I said, I got plenty of examples to go through so you can see this method over and over. about the integral of tangent x dx? We know what the integral of secant squared is. It's tangent x. We know the integral of secant tangent. It's secant of x. But we don't have an integral of tangent. What we're going to do here is we're going to rewrite this as sine x over cosine x dx. I'm going to let u equal cosine of x, because then when I differentiate this, du is equal to sine of x dx. Now I'm going to plug everything in. Let's see, so this equals integral. Oh, I got to solve for dx. So divide by sine of x, divide by sine of x, du over sine x is equal to dx. So now, plugging everything in, this becomes 1 over u, or sorry, sine x over u times du over sine x. The sine x's cancel, and you just get the integral of 1 over u du. I made a slight mistake. I'm forgetting a negative sign here. The derivative of negative cosine, or sorry, cosine is negative sine. So I'm dividing by a negative sign here. So when I divide by a negative sign here, there's a negative out front. Forgot the negative. Hey, we just integrated that a little bit ago. Negative ln of u plus c. Then I'm going to take my u, I'm going to plug it in. So you get negative ln absolute value cosine of x plus c. So they usually write this in a different form so we could get our final answer. What they typically do is they bring this negative using this -1 using the properties of a logarithm up into there. So this becomes ln of cosine to the negative first power, not negative first power, to -1, there we go, plus c. This is the 1 over cosine, so you get ln of 1 over cosine x plus c, which is ln of secant x plus c. So the integral of tangent x is ln of secant x. Now, let's quickly talk about the integral of cotangent of x. You may be able to guess on what the integral of this one is based on that one. Let's go ahead and take a look at the derivatives. Tan x, if you take the derivative of that, was secant squared x. Cotangent x, if you take the derivative, is negative cosecant squared of x. So tangents are related to secants in the derivatives. In the integrals, tangents are related to secants. If you recall, cotangent is just cosine x over sine x. You would go through and do the same procedure. You would let u equal sine of x, du equal cosine of x. You would go through and differentiate, use substitution. But this integral right here, ln of cosecant x. So if tangents are related secants, cotangents are related cosecants. Integrals of cotangents should be also related to cosecants. Let's see, another problem. Integral square root cotangent x times cosecant squared of x dx. Now with our discussion just a little bit ago, this should help you figure out what the inside of the function is. I just had cotangent of x, the derivative is cosecant squared of x. I just had it written down there. So that might help you figure out what the inside and outside function is. This is the inside function, that's the outside function, because by the chain rule, if I were to take the derivative of the cotangent, I'm going to get a cosecant squared. So u is equal to cotangent x, differentiate that, you get negative cosecant squared of x dx. Solving for dx, I'm just going to write it up really quickly, is negative cosecant squared of x. So let's make our substitutions. Just plugging them in. We get the integral of square root of u times cosecant squared of x times du over negative cosecant squared of x. The cosecants cancel. You get, I'm going to bring the negative out front, negative integral of u to the 1/2 du. Well, that's just the power rule. You get negative 2/3 u to the 3/2 plus c. Just undoing the power rule. Go up 1, you get 3/2. Divide by that coefficient, it flips, you get the reciprocal, you get 2/3. So now just plug in your cotangent. So the final answer is negative 2/3 cotangent of x to the 3/2 plus c. Very simple rule. When I say simple, I mean in comparison to the other integration techniques you learn in Calc 2. Alright, let's see. Let's do one more. Integral of x times 2x plus 5 to the 8th power dx. Now this one's a little tricky. This is going to be our inside function. U is equal to 2x plus 5. Du is equal to 2 dx. So if I solve for dx here, you get 1/2 du. Let's go ahead and plug in our substitutions. Well, I've got x times u to the 8th times 1/2 du. We have a problem here. Normally in all the previous examples, this dx, when we plugged it in, always canceled with any extra x functions left over. The x function didn't cancel this time when I solved for dx and put it there. So I can't integrate this right now. I have to get rid of the x. How do I get rid of the x? Solve for x here. Solve for x here. So if I were to do that real quick, x is equal to 1/2 u minus 5. So I'm going to take that and I'm going to plug it in right here. So I get integral, so 1/2 u minus 5 to the, not to the 8th, u to the 8th times another 1/2 over here, du. Now all my x's are gone, which is really nice. If I multiply this out, integral, there's a 1/2 times a 1/2, that's a 1/4, times, distribute this, you get u to the 9th minus 5u to the 8th du. So again, this is just the power rule. We've got 1/4 out front. See, this is a 1/10 u to the 10th minus 5/9 u to the 9th plus c. So just undid the power rule. Go up 1 power, you get a 10. Divide by that power, you get a 1/10. Go up 1 power, so 8 goes to 9. Divide by that, so 5 divided by 9. And then we still got the 1/4 out front. So now all we have to do is take our u and plug it back in. So we get a final answer of 1/4 times 1/10 2x plus 5 to the 10th minus 5 over 9 2x plus 5 to the 9th plus c. Let's see, let me erase some stuff. So there's our final answer when plugging back u into there. Now you could distribute this 1/4 everywhere. You can leave it out front, that's fine for now. But you should go ahead and pause the video, go ahead and try those 2 problems that I gave you for u substitution, and then you can come back and we could talk about the substitution rule for definite integrals, okay? So the substitution rule for definite integrals is very similar to just normal definite integrals. What this is saying is if we're integrating from a to b now of f of g of x times g prime of x dx, when we make this substitution u is equal to g of x, and we write our limits of integration here, the lower one is going to be g of a, the upper one is going to be g of b. So upon changing into a different variable into your u variable, the limits of integration also have to change, because these limits of integration are from x equals a to x equals b. This is from u is equal to g of a, u is equal to g of b. So you cannot use your normal limits if you're still in the u variable. You have to use the u limits. Now if you switch back, at the end of every problem, we always switch back to the x variable. If you switch back to the x variable, you could use your x limits. Okay, so all this is saying is that if you want to integrate this, a definite integral, it's exactly the same thing as what we were just doing. You have to evaluate it at the endpoints, but they're different endpoints than what we have here. We have to find them by plugging them into our u equation. Now, it doesn't matter which way you do it. You can get these numbers, plug them in, or you can plug in your x variables and then plug these ones in. I'm going to show you both for this first example, and I'm going to show you how we get the same answer for both of them. It doesn't matter which way you do it. So, it's the integral from, let's see, 1 to 2 of e to the 1 over x divided by x squared dx. So, I'm going to let u equal 1 over x. That means du is going to be negative 1 over x squared dx. So then when I solve for dx, I get negative x squared du. Just multiply both sides by negative x squared. Let's go ahead and make my substitution. Now I'm going to write the integral sign. I'm not going to put my limits though. We're going to wait for that. So you get e to the u over x squared times negative x squared du. The x's cancel. You get the integral of e to the u du. Now, if we want to put limits of integration on here, we have to transform these limits of integration. So, plugging in 1 into here, you get u is equal to 1 over 1, sorry, not 1 over x, 1 over 1, which is equal to 1. So, coincidentally, the lower limit stayed the same. But now if I plug in 2, u is equal to 1 over 2, well that's 1/2. So in the x variable, the limits of integration go from 1 to 2. Upon this variable change, and we write everything in terms of u, we write our integral in terms of u, the limits of integration must change as well. Coincidentally, when you take the 1, this is x equals 1, x equals 2. If I plug them into my substitution, again, coincidentally, this just remained a 1. That does not always happen. But this is a 1/2, because I plug 2 into here, you get 1/2. So integrating this is very easy. E to the u evaluated from 1/2 and 1, which is e to the 1/2 minus e. That box. So there's our answer. That's our answer in the u variable. Okay? Let's go ahead. We already have our antiderivative, but let's say we wanted to keep it in terms of the x variable. So all I'm going to do is plug in my u, so I get e to the 1 over x evaluated, but now since I'm in terms of x, I'm in terms of my x variables, I could use 1 and 2. Well, let's go ahead and plug it in, and you're going to see we get the same exact result. E to the 1 over 2 minus e to the first. The upper limit evaluated minus the lower limit evaluated. Hey, look at that. They're the same answer. So what this allows us to do is after we transform the variables, we could take a definite integral. Sometimes evaluating this definite integral is a little bit easier because there's less clutter. Like this looks really messy compared to this. This is really nice. Okay. Sometimes you want to switch back to your original x variable because maybe you need the function or whatnot. But either way will get you the same result. The common mistake here is keeping the same limits of integration when you switch over to your u variable. I've seen this on students' papers when I tutored. 2. So then if I put a 2 here, it's going to be e squared minus e to the first, which is wrong. Okay. So pick which one you want to evaluate your limits in. Okay. Me personally, I always switch back to my x variable, and I always plug in my x limits of integration. I would say just be consistent in what you do. That way you don't mix things up. Like you accidentally put these limits here because you want to do it in terms of u this time. In a different time, maybe you want to do it in terms of x, but you accidentally put your u limits. Just be very consistent about it, and I don't think you have to worry. So let's go ahead and do the next example. It'll be the last example of this section. The last part of this section, even and odd functions, integral of even and odd functions, just like more informational, something you should see, just be aware of. So let's see, this is the integral of 0 to 1 of the cube root of 1 plus 7x dx. U is equal to 1 plus 7x. Du is equal to 7x, not 7x, 7dx. So if I solve for dx, I get 1/7 du. Here's my u, took the derivative, solved for dx. That's all I did. Let's go ahead and plug everything in. So I'm not going to write my limits of integration right now. This is cube root of u times 1 over 7 du. So this is 1/7, bring the constant out front, u to the 1/3 power du. Again, it's a very simple power rule that we can undo. Let's go ahead and do this one in terms of u. We will do it in terms of x also, but let's do it in terms of u. Let's find our u limits of integration. So u is equal to 1 plus 7x. Well, x equals 0 and x equals 1. That just means plug in 0 into here. If I plug in 0, you get 1 plus 7, or sorry, 1 plus 0 is 1. Now let's plug in 1. 1 plus 7, because 1 times 7 is 7. 1 plus 7 is 8. So this integral right here is equivalent to this integral. Notice I changed the limits of integration. Let's go ahead and integrate it now. 1 over 7 times, this is going to be u to the 4/3 power, but then multiply or divide by this power. So you get 3 over 28 u to the 4/3 power. And what we're going to do is we're going to evaluate that at 1 to 8. So starting at 1 to 8, using my u limits of integration. So you get 3 over 28 times 8 to the 4/3 power. 8 to the 4/3 power minus 3 over 28. And you just plug in 1 into here. You just get 3 over 28. 1 to any power is 1. So this is 3 over 28 times, I could factor it out, 3 over 28, 3 over 28. 8 to the 4/3 power is 16 minus 1. You get, this is 15. So you get 45 over 28. 45 over 28. There's our final result. Let's go ahead and do this in terms of the x variable. Let's see if we get the same answer. So, let's see. Here was our antiderivative right there. Let's go ahead and write this over here. Plugging in my x variable, you get 3 over 28 times 1 plus 7x to the 4/3 power, evaluated from 0 to 1. Well, if I plug 1 into here, you get 3 over 28 times, plugging 1 into here, we get 8. 7 times 1 is 7, plus 1 is 8. 8 to the 4/3 power minus, well, if I plug 0 into here, well, hold on, 3 over 28. If I plug 0 into here, you get 7 times 0 is 0, plus 1 is 1 to the 4/3 power. Well, 1 to any power is just 1. As you can see, 3/8, 8 to the 4/3. Sorry, I said 3/8. 3 over 28, 8 to the 4/3. 3 over 28, 8 to the 4/3. Minus 3 over 28, minus 3 over 28. So, just to reiterate, you could find these definite integrals in terms of u, or you could find them in terms of x's. The thing you need to watch out for is to make sure you're plugging the right limits of integration into the correct function. If you're in terms of x's, use the x limits of integration. If you're in terms of u, use the u limits of integration. Alright, so the last part of this section, we're not going to do anything with it, but like I said, it's just informational. It's integral of symmetric functions. Let's talk about an even function. An even function, here's by definition what even function is. F of negative x equals f of x. If you plug in negative x, you get back with what you originally started with. Now, if I were to say the integral from negative a to a, notice it's negative a to a, so that means if we were talking about a function, you start over here, you start over here, they're the same distance. So of f of x dx, so we know that this function is even. Let's draw an even function. A parabola is an even function. This could be something like x squared plus 4, where right here is 4. Now think in terms of area. It's that area plus that area. Aren't those two areas exactly the same? You've got this area, this distance negative a away, this distance a away. They really are exactly the same. So a different way of computing this integral for even functions, if you know your function is even and you're going from negative a to a, this is the same thing as the integral from 0 to a of f of x dx. So now we're just starting here. We're going to a. Since there's two of them, we put a 2 out front. So we could always rewrite the integral of an even function as long as we're going from this negative lower bound to a positive, the same upper bound. Now let's talk about an odd function. So, for an odd function, f of negative x is equal to negative f of x. So if we were to do that same integral from negative a to a of f of x dx, we know that f is odd. Well, this is going to equal 0. Let's see why. Let's look at the sine function between negative pi and pi. Well, you've got that area down there, which is negative. That area, which is exactly the same area, but positive. So if you're integrating an odd function from some negative a value to some positive a value, all the negative area is going to cancel exactly with the positive area. So it's always equal to 0. Like I said, I'm not going to test you guys on any of the even odd function integrals of them, but it's something you should see before you move on to next classes, because it gives you a nice little tool to evaluate integrals a little bit faster by knowing properties like this.